Welcome everyone. Now I have just started the recording of today's presentation, Bridge Foundations at Large Water Depths, and the presenter is Joar Tistel. The recording will be put online afterwards, and it will not show who has participated in the meeting, but it will show if you ask questions at the end, and there is an opportunity to ask questions when Joar is finished. So, the floor is yours, Joar.
Thank you, Kjersti. So, this presentation is about bridge foundations at large water depths. This study was started in October 2014, and this thesis was delivered 3 years after. And the defense was organized in February this year, so it's half a year ago. Thank you for letting me present today. The supervisor was Professor Gudmund Eiksund. The co-supervisor was Anders Rønqvist. And I also had assistance from Professor Gustav Grimstad on this work. First, I will say a few words about the background and the problem definition. This presentation today is basically the same presentation as that I had at the defense. I have shortened it a bit to fit to 30 minutes. I'll try to at least. The second topic, or the second of the contents today, is the first research topic, which is rock anchors. Rock anchors subjected to cyclic loads. I will first give a general introduction, then I'll show you a few slides about the laboratory work, results, and modeling. Thereafter, it's the research topic number 2, which is macro modeling. First, the introduction, modeling itself, and the validation of the model, which we did by model testing in the laboratory at NTNU. So, first on the background on bridge foundations at large water depths. So when I started this study, I did have a good basis for offshore geotechnics, but I did not know too much about bridges and bridge design. So I therefore started up with a study on large bridges, and I started with I have a few examples here. This is the Storebelt bridge. The main cables, they are anchored to an offshore gravity structure installed at some 12 meters of water depth. The main span is about 1600 meters. And if you look at this figure, we see the bottom weight is about 1900 meganewtons. It means it's a quite large structure. It's 120 meter long and about 50-60 meters wide, so it's a huge footprint. The cable pull is about 500 meganewtons total. Large forces. Another interesting object is the Nordhordlands bridge, which is a curved floating bridge with a tall bridge at the south side. The abutment at Klauvaskallen is a gravity structure utilizing rock anchors to increase the in-place capacity. As this figure, you see the gravity structure placed on rock, and you can also see a few rock anchors below. Another interesting bridge is this Akashi Kaikyo bridge in Japan. Cable pull of 1.2 giganewtons. That's quite a large load. And you will also require a large foundation structure to hold this load. This foundation is a gravity structure of about 85 meters diameters and 75 meters deep. So we can conclude that you will require quite large foundation structures to hold these forces. Another interesting topic on background is if you look at the geology at the west coast. We can look at this picture. It's a beautiful picture from the west coast. It's my family's cabin back home. You're looking at now, but it's typical for the west coast. You see the tall mountains, the steep valleys, and the deep fjord. This place is about 1,200 meters deep, and within the fjords you have soft sediments. So there might be challenges also related to that if you want to place a fixed structure, or if you will anchor structures. So on the problem description and the motivation for this work, initial assessments concluded that, well, if you have a large bridge structure, you will have large forces, which will require large foundations. There are challenging site conditions, looking at the geology along the west coast, and there are numerous load cases to be analyzed. So I had these research questions. How can we reduce the foundation size? And how can we improve the design process? This led to the following research topics. Rock anchors subjected to cyclic loads. And the motivation here is that rock anchors may reduce the required foundation size, like this, and thereby reduce costs. And the second topic, that is that a macro model describing the nonlinear foundation behavior. And the motivation here is that the macro model may improve the soil structure interaction analysis. So the macro model represents the nonlinear foundation behavior in one single element. So both of these topics, they concern foundation design of bridges, but also other foundation structures in general. And foundation capacity is one of the prime topics within geotechnics. And a larger foundations mean larger capacity, but it may also imply a larger cost and a negative schedule impact. So effective means to reduce size may constitute both rock anchors and calculation models, which can predict the necessary foundation sizes more precisely and thereby reduce excessive redundancy. So that's the motivation on this work. So if you look at the first topic, which is cyclic loaded rock anchors, first you will have some introduction to rock anchors. I will present the laboratory test setup that we use to test our model anchors, interpretation of results, the model development, and implementation of the model. And this work is presented, of course, in the thesis, but also in 3 papers. First, the rock anchor, as it is presented in the Eurocode. They can be either pre-stressed or passive. Main components of the rock anchor is, of course, the borehole. It's the anchor bar or strand itself. We have the anchor head, the fixed length, where the anchor is fixed to the surrounding rock through the grout. We have the free length, which is necessary if you want to mobilize deeper layers within the rock, the deeper rock volumes. And Traditionally, we are looking at 4 failure modes for a rock anchor. There is a failure within the steel itself. It's the steel grout interface failure. You pull it out from the grout. It can be the grout rock interface or the rock mass uplift. This study concerns one of these failure modes, and that is the steel grout interface. So there is a limitation within this work. Traditionally, when rock anchors are designed, you can use an average shear capacity along the anchor. That is simplification. If you look at how it really works, is that if you pull the anchor a little bit, you will mobilize shear along the anchor until ultimate bond stress, a peak value at some slip or displacement, which we define as S1, and the ultimate bond slip is tau BU. If you continue to pull the anchor, looking at the section of the anchor, then the capacity will drop until you meet a residual bond stress, tau F, at a certain distance or slip, S2. That's kind of a definition of a 3-linear bond slip model. So it is not a constant shear stress or shear capacity along the anchor interface. So in order to define these values, we have to do laboratory testing. And the laboratory test setup looks like this. In this setup, we can do both, say, monotonic testing and cyclic tests. So if we take a look on this section, we have a hydraulic jack, a hollow jack. The bar is protruding through this jack, and we have a fixation on top and a load cell below this fixation, so we can measure the applied force. We have the steel bar, which is installed in a pre-drilled hole into a large concrete block, and we have the grout. So the model anchors that we have tested at the laboratory is 17.5 millimeters diameters, and the pre-drilled hole is 50 millimeters. We have we have the hydraulic pump, which apply the pressure to this jack, and we have flow control valve where we can control the pressure or the force on the anchor, and thereby we can apply both. We can apply any load characteristic which we want in principle, cyclic or monotonic. Monotonic tests, they were performed to define the ultimate bond stress, tau BU, at this point. Define the slip value at tau BU, and you can see we have defined this slip as SR1, which is residual slip. It means that we have subtracted the elastic displacements. That's why this line is inclined. And we define the bond slip envelope, which is this black curve. Cyclic tests, they were performed under constant load amplitudes, load control, frequencies between 0.2 and 0.5 Hertz, depending on the load level. And we measured displacement or slip as we performed this test. Observations that we did, we see that the maximum bond strength did not reduce as long as the slip is less our rock anchor to the peak value tau BU, as long as we have not passed this slip line. It means in principle that the capacity is not reduced even though we have a significant amount of cycles on this left side of the dotted line. The slip per cycle decreases until SR1. You can see the density of these load cycles increases until this line, and then it decreases after. So the resistance towards cycling increases until you meet this line at SR1. The cyclic bond slip pattern remains within the monotonic bond slip envelope. So this is the monotonic bond slip envelope, this black line. So these cycles will remain within this envelope in this figure. On the modeling, we have based the modeling on two equations. This can be found in the thesis. I will not go into very much detail in this presentation. Only it's interesting to know we have based it on two equations. First one looking like this, modeling the first part of the bond slip. What we are looking at in this figure is number of cycles on the horizontal axis and slip on the vertical axis. So if we apply cyclic loads on, with a constant load level, constant amplitude on a rock anchor, it will, in an N slip diagram, it will look like this. The lower part is the plastic slip, whereas this upper part is plastic plus elastic. That's why we have this band. So the first equation models this curve until you reach SR1. And the second equation models the last part from SR1 until failure. Our model is then implemented in the software ANSYS, a finite element code. You can see this purple color indicates the rock anchor, and our model is implemented within the interface along the rock anchor. And we have used a plane strain axisymmetric model. And the inter-element offers direct means to quantify the interfacial separation behavior. So this is a picture from one of the anchors that we tested, short section of anchor. We tested both short and relatively longer anchors. These short anchors are used to define the ultimate bond and SR1 values. We also tested or modeled 500 millimeters anchor, constant cyclic load amplitude at 300 kilonewtons at anchor head, and we can plot results. First figure here is the length along the anchor, so 0 to 500, it's 500 millimeters long. At 500 we have the anchor head where we apply the force. On the vertical axis we are looking at displacement. So the displacements are largest at the anchor head, and we have plotted these lines illustrates numbers of cycles. 10 cycles. After 10 cycles is this lower line, and then we have 20, 100, 1000, 10,000 cycles up to 130,000 here, where we have the failure. The lower figure illustrates also length along the anchor, but then we see the mobilized shear along the interface. So that's after 10 cycles, 20 cycles, 100 cycles, 1,000, until we approach a failure. So these things we can model, yeah, but it will look like this. If I speed it up a little bit. At the upper left you will see time, which is number of cycles, 1600, 2000 cycles and so on. And we are looking at vertical displacements, so we are pulling out this rock anchor from yeah, the concrete or the rock. If we speed it up a bit, we will see that finally it will pull out like that. So on this work, on the conclusions, on rock anchor and modeling, we have modeled the slip per cycle as a function of the cyclic load level. The R, which is the ratio between minimum cyclic load and maximum cyclic load, or shear stress. It's a function of SR1, the slip at tau BU, and the beta, which is input to the number of cycles to failure. So the beta is also an input value into the model. N2, number of cycles to failure. This equation is based on the Aas-Jakobsen equation for concrete subjected to cyclic loads in compression. So we have used the same equation and only fitted the beta value. The model is developed for a section of a rock anchor. And if we then have a long anchor, we we can use FE code, and we have used ANSYS. Industrial practice is to use average shear value, which is a safe and conservative approach. This model, this new model, is conceptually more correct. It's based on a constitutive bond-slip relation, and it is verified by testing. But as for any other model, there are certainly limitations. Long-term effects in terms of creep versus cyclic damage, it has to be separated. The model is prepared for it, but it is not tested for it. The failure mode, we have been looking at the grout and bar or rock anchor interface, but you can also have the failure along the grout rock interface. We have cycled from 0 to tau max. We do not have a tau min, so it is not calibrated to a tau min value, but the model is prepared for it. Documentation on long anchors. We have tested relatively short anchors. And there are more. So, future use of rock anchors, subsea perhaps. It can be used for bridge foundations offshore, like this, to reduce foundation sizes. Perhaps for submerged floating bridges. And more. So that was rock anchors. On the next topic, which is the soil structure interaction, which is the macro model. On the topic of soil structure interaction and the macro model, we have investigated the SSI calculation methods which may improve the design process. And this concept of macro model, it has been pioneered within the offshore industry, and now also within the offshore wind industry. So we have introduced this into the concept of a bridge design. We'll first have a short introduction to macro models, and we'll look at a case study and the laboratory testing which we did for this work. It's also published in papers which I've called 2, 3, 4, and 7. It presents both theory and laboratory work. It's all enclosed to the thesis. So how the macro model works, it's the nonlinear foundation behavior, which is represented by one single element. And vertical load eccentricity and inclined loads are reduced to 3 load components together with corresponding displacements, like that. And these models, they apply classic plasticity theory, which is used to describe metal behavior. And the model use yield surface, elastic domain, and a flow rule, and a hardening law. Yeah. So how this concept works is illustrated by VHM, that's vertical, horizontal, and moment loading on a foundation, like that. So we have a yield surface wherein elastic displacements will occur if the load state is changed, and we have a potential surface, a flow rule, and a hardening law. So if we have a load state illustrated by this point, a certain vertical load, and we then load this foundation in the VHM space, we can follow these dots, and the model will then result in nonlinear displacement, like this. You could start loading, and then we have the plasticity theory. On the background, 3D yield and failure surfaces are developed based on the work related to interaction diagrams. A lot of this work were done in the 70s, 80s, and now it's taken further. And such diagrams, they define a region inside which all of allowable load combinations must lie, like a MN diagram for a column or whatever. And results from laboratory tests, they are used to define these interaction diagrams. And you use parabolic shapes to model these curves. And you also can do a swipe test to define the shape of these curves. A swipe test, first the footing is placed, the footing is loaded with a pure vertical load until it reaches a prescribed load, like that, V0. And the swipe test is thereafter initiated. You do like that. You lock it in vertical direction, and you start to push it, and you will follow the failure surface, and thereby define this shape of the yield surface. Rotation or horizontal displacement is then applied, like when you do this. And the trace of these forces, this yellow line, corresponds to the track along the yield, a track along the yield surface. And you also have to calibrate the other parameters in the model. You can do that by FE program, either 3D linear elastic analysis for elastic parameters, and 2D analysis for yield surface, swipe testing like we saw on the last slide, and you define the potential surface and the hardening. So you can, we used FE calculations to define the surfaces, as you see from these lines here, and we arrived at the calibrated yield surface. We did a calculation example. We just took an anchor block calculation case, and we tested our macro model towards finite element program, and we had, I would say, a very good match. In geotechnical terms, it's a very good match comparing to the FE code. So we applied cable force, which will then act with moment, horizontal load, and we do have a vertical load component at the center of the foundation. So this is what we are looking at in these three plots, which is the vertical load with vertical displacement, moment with rotation, and horizontal load with horizontal displacement. We validated our macro model with laboratory tests. First, we calibrated our model by use of finite elements. Thereafter, we performed the laboratory test and compared the results from the laboratory with the macro model estimate. So the test rig itself, it was, you can see it also on this picture. It's a steel frame hanging over, or it's fixed to the edge of the sand bin. And then we have our model foundation, our prototype foundation, this box, steel box. It's 0.4 meters by 2.2 meters, this box. The sand bin itself is 4 by 4 by 3 meters. That's 3 meters deep. The load is applied by ball screws, and we have load cells connected so we can control the system. The testing is performed in horizontal load and moment load plane. So this is, you can see the ball screws, these black cylinders, horizontal load applied by this one, moment loading or rotation applied by this one, and then we have the vertical load. And again, we calibrated our model to, we model our prototype foundation in Plaxis FE software with the correct soil properties and so on. Found the yield surface and the potential surface. And then we tested the foundation in the sand bin. What we're looking at here is the horizontal load, moment load plane. And we have this typical ellipsoid shape, which you will see in such a plane with some eccentricity. And then we compared our macro model results with the laboratory test results. So on the figure to the right, you see the macro model test result with these dotted lines comparing to the laboratory test, the prototype test. And we find also a very good match on this test. The figures to the left is first, the upper one is the moment with vertical displacement. It's the horizontal load with horizontal displacement, and it's the moment load with rotation. So a conclusion on the macro model, it compared well to the laboratory test results, and the model were also able to reproduce uplift behavior. It means that for a certain eccentricity or a certain moment, the center of the foundation will start to lift. The model can be used for shallow foundations on granular materials. That's what it is developed for. And the model may significantly streamline soil structure interaction analysis. General engineering impact on the topic, on the first topic, modeling of cyclic loaded rock anchors. We have shed light on important aspects of the rock anchor capacity and how to model it. The model may be applicable for instance, wind turbines onshore or offshore, nearshore or offshore fish farms, floating bridges, rock bolts in the mining industry, rebar in concrete. Well, it is more or less a rebar in concrete what we have tested, so why not? And more. On the second topic, it's on the macro model. We have validated a model for shallow foundations on sand. It can be used for subsea templates, gravity anchors for floating structures, gravity structures in general, shallow foundations. And then in the defense, I also had to give some conclusive remarks. Yeah, it was two main topics. It was the cyclic loaded rock anchors, macro model. We have worked these problems both through theoretical work and experimental work. I think that's a very good way to do the research. We have documented the theories and the models through the through laboratory experiments. So that's very good. We have proposed models for both topics. Yeah, and we have validated the models. And well, that's it. And I also want to say thanks for all of those who were involved in this research, especially to 3 master students who delivered their thesis based on working on this topic. Thank you.
Thank you, Joar. And then we are open for questions. Do we have any questions? You can do them in writing or you can just speak up.
Hello, this is Adil from Vajdirektoratet. I have a question. Can you hear me?
Yes,
Yes.
please go ahead.
Yes. What are your concluding remarks about future work to put these findings into practical use?
Yeah. We have tested our model on short, very short anchors comparing to what is used in practice. And there's also small diameters. And it's the interface between grout and rock anchor. So one important topic is to investigate what happens at the rock grout interface. I have briefly been looking into cyclic loading of rock and rock volumes, and it seems to be, I would say, comparable. So it might be, I think that the model can be used also along that interface, but it probably will have to be calibrated, for instance, with the number of cycles to failure and the tau BU, probably. But then it's also on the size of on the scale of things. We have been working with a small scale anchor. If you go out in the field, there might be there will be large scales, 4, 5, 6 meters of anchored zone. Still, I think that the theories that we have been and the model that we have developed can be feasible also for those anchors, but one will need to define the correct input values, like the ultimate bond, slip at ultimate bond, and the beta value, which describes the number of cycles to failure.
Thank you.
Thank you for the question. I think that we have also listed some suggestions for future work at the end of the thesis. Recommendations for future research. Yeah.
A small question. Is there any specific reason that you kept this R value to 0.6, the peak ratio between maximum and tau value?
We have the R value is 0. Did you see 0.6?
The ratio between the what you call normalized bond.
Oh yeah, okay. No, that's only an example which you saw in that plot.
Okay.
Yeah, so we tested for the whole range, so to say.
Okay.
Yeah, we had to do that to get our model correct. But the minimum load, we always cycle down to 0. Yeah.
Okay, do we have any more questions? No?
If nobody is asking, I can ask one more.
Yeah, sure.
Please go ahead.
That's good.
The interface roughness between steel and concrete, the maximum value for that, what was that from your test results?
Well, we that's the value of the ultimate bond stress itself, I assume. Yeah, that's
I was thinking more like if it was like 100% mobilized, or it was like we use a factor in practice nowadays, like 2.6 or 0.7, depending on the grundforhold around the anchor. But that factor I'm asking about.
But then you apply that factor on ultimate bond on a capacity. Yeah. So we just applied we measured the bond capacity, and we used that directly without any factor. Yeah. So we use characteristic values. But those values, for the test setup that we had with the 17.5 millimeter rebar or rock anchor, and the grout that we had a value of 17.5 or 18 megapascals tau BU peak value.
Did you try any modeling pre-stress, like permanent stress and cyclic loading on top of that?
No, that was decided before we started, that we were only testing passive anchors because of practical reasons.
Okay.
Yeah.
Thank you very much.
Yeah. Thank you.
And thank you. And do we have any more questions? This is your chance. No? Then I think I will just use the opportunity also to remind everyone that next Friday we have another presentation, wind tunnel testing combined with wave loads for extreme bridges with Henrik Skjulstad. So you're welcome to come back next week. And Joar, thank you very much for a very interesting presentation.
Thank you. And if there are any questions later, feel free to contact me.
Yes. Okay, so then I stop the recording.